Good morning. My name is Alfredo Milani, and this is a joint work with Valentina Poggioni and Riccardo Queri. In this presentation, we will introduce the network immunization problem. We will discuss state-of-the-art issues which arise with scale-free network and the autonomous-oriented computation approaches to immunization. And our proposal, the general stochastic self-regulating algorithm. We will present experimental results and we will draw some conclusions. Network immunization problem. Network immunization domains include social and collaborative network, financial network, computer network, the World Wide Web, as well as communication network, like the airlines network shown below. The network immunization problem considers a graph GVE, and the problem is that the network can be infected, usually by computer virus or other kind of infection, and the infection can spread all over the network using the links, eventually invading the whole network. Network immunization strategy aims to stop the spreading by immunizing the vertices, that is to say, to place some kind of shields on the network nodes in such a way that the network virus diffusion can be contained. Although it would be the ideal solution, a complete immunization of all network nodes is not possible for different reasons. The main reason is the network dimension. The network we are considering our largest network. And the second big reason is the cost and the speed of the immunization process. We want to immunize the nodes as soon as possible, the most relevant nodes, in order to block the spread of the virus. So time is a very important variable in this kind of problem. Random immunization is a very simple and efficient algorithm, but unfortunately it works only in the case of uniform network. In the case instead of scale-free network, that is our case of interest, random immunization algorithm needs to immunize nearly 100% of the nodes, so they are not really viable. Target immunization instead use the approach of immunizing only a subset of nodes, namely the most connected nodes, the highest degree nodes in the network. It's been shown that the virus can be eradicated by immunizing 7 to 10% of the highest degree nodes in the network. This algorithm is very efficient with scale-free networks, but the drawback is that it's a global strategy that requires to know the whole network and its topology in order to determine which are the highest degree nodes. This step immunization applies the idea of the targeted strategy in a distributed style. The main idea is to select the highest degree nodes in a neighborhood of radius d of a set I of initial random nodes. The D-step immunization strongly depends on the initial value of d and on the initial set I. Moreover, another drawback is difficult to escape from communities. Communities are clusters of highly connected nodes, and community arise very often in the case of social network and scale-free networks. Autonomous-oriented computation approach and self-regulating approach overcome this problem of escaping for the community. We will have more detail in the next slides about these two approaches. The idea of autonomous-oriented computation is to deploy a set of n autonomous entities on the network. Entities are able to explore the network to find the highest degree nodes and place themselves on those nodes in order to immunize them. The approach is completely distributed. That means there's no centralized entity, no centralized control, and it depends only on the initial number of entities placed on the network. So the idea of the IRC approach is to place entity in nodes, like entity E1 in the figure. The entity is doing a local search on the local environment. The local environment consists of both direct and indirect neighbors of the current nodes, and the entity is behaving according to certain behavior rules, which are basically three. A rational move takes place when the entity moves from the local node, the current node, to a node with a better degree, like the one in the figure. A wait move that is doing nothing, and this is done when the entity don't see any nodes in the neighborhood which improve its current degree, and the random jump which take place in certain situation to avoid the entity stuck in a local minimum. Here is the AOC algorithm, which is basically describing behavioral rules of the entities. And this is done by using two concepts, utility and life cycle. So the utility is basically the degree of the nodes which are occupied by the entity. And whenever the degree of a nodes in the neighborhood is improving the current degree, then the entity make a rational move. That means goes in that node. The life cycle instead is used to avoid to wait too much on the same nodes, which is probably a cue that nodes is a local minimum. Life cycle is incremented every time utility increase, that means every time you move, and is decremented every time wait action, no action is applied. So when life cycle goes to 0, then a random jump takes place. So there are some issues in this algorithm which has been proved state of the art. The main problem is that the algorithm assumes that some information are known about the network. For instance, the algorithm places a certain number n of entity in the network. So, in other words, the algorithm assumes to know the number of nodes of the network in order to decide the immunization rate. The problem is that if n is too low, there is the risk of infection. No enough entities are placed on the network. If n is overestimated, then you waste resources. For instance, you waste the occasion to immunize other networks. In the self-regulating approach, we try to overcome this problem of knowing beforehand the number of nodes in the network. So we eliminate the dependency on the initial number of entities, and this is done by introducing a new action or behavioral rule that is reproduced. So the idea is that the entities can reproduce themselves until their population is enough to reach a given immunization rate. So in this approach, only few entities are deployed in the network, and then the entities explore the network and reproduce themselves as needed. The key feature of the self-regulating algorithm is the local distributed estimation of immunization. And this estimation is based on the entire history of observation that an entity has made, and is triggering the entity reproduction under certain condition. The condition is that an entity can reproduce itself when the estimated immunization is lower than the immunization target that we want to reach. How the local estimation works? It depends on two pairs of values. E-obs and N-obs are respectively the number of entities and number of nodes which has been observed by entity E until time t of its lifetime. ET and T and NT and T are the same concept, number of entities and number of nodes on traces. Traces are information left behind by entities on nodes in order for other entities to use in the future. An entity is allowed to modify ET or INT if it's more trustful of the previous entity that has modified them. So an entity is considered more trustful if it has more experience, if it has observed more entities or more nodes in its lifetime. There are three factors which characterize the reproduction strategy in self-regulating algorithm. First one is branching factor. Branching factor decides the number of entities which are generated as an offspring of one entity when it reproduces. Inheritance. Inheritance is the knowledge that is inherited by a new generated entities from its parent. In this case, we decide to make inherited the utility parameter. The utility is the value of the highest node, of the highest degree nodes that an entity has ever met in its life. Position. Position is where to place the new entities, either in neighbor nodes or elsewhere. So we decide to make a random jump action every time a new entity is generated in order to privilege the exploration behavior of the algorithm. Experiments have shown that the self-regulating strategy is performing well in some cases, worse in others. For instance, in this graph we show the parameters coverage in red, immunization rate and reproduction rate in blue. So we observed that in the case of Nutella the performance are pretty satisfactory. The target is 15% and after 10 steps the target has been reached with 100% coverage. On the other hand, in the case of Facebook, we observe that after 10 steps we are way over the target, thus exploiting, wasting resources. On the other hand, we also observe that the number of entities which reproduce is still high, so the immunization rate is growing over the time, which is not that we want. So the objective of our works was to define a new reproduction strategy in order to regulate the behavior with respect to the target immunization rate. What we want is that the target immunization will be reached as much as close as possible and doesn't increase indefinitely. So we want some kind of stable behavior. So the key point that we were working on are improving the local estimation of immunization rate and to change the strategy in order to produce less entity and avoid this phenomena. There are different novelties in the SSR strategy. First of all, stochastic reproduction is used. A new definition of trustness is provided. Branching factor is dynamic, and the type of knowledge which is inherited by offspring is different from the previous case. In SSR, it's not used a deterministic reproduction, but reproduction depends on probability PRET that is determined by the ratio between the estimation made by the entity E at time t and the target immunization. The new trustness concept of entity consider an entity more trustful than another one if it has explored a larger portion of the graph. That is to say, has been doing a larger number of random jump or rational move. The branching factor is also dynamical and it depends from the local estimation made at time t by entity E. Factor K is the initial branching factor from which an entity starts, and this factor is not inherited unchanged. The reproducibility of a offspring, in fact, is divided by 2. This leads to an exponential smoothing of the reproduction rates in the entities. Experiments shows that the self-regulating strategy is improving the situation for certain domains. For instance, here in Facebook, CondMat and HEFH, we observed that the coverage rate after 10 steps is over 90%. That is quite satisfactory. As well, the immunization rate is quite close to the target. On the other hand, we still observe we have this phenomena of growing the immunization rate on the long run. That means we are wasting resources, and on the other hand, it means that some entities are still reproducing themselves. Cases, unfortunately, for instance, here is the example of Nutella Wikipedia. After 10 steps, we reach an immunization rate, a coverage of 100%, while the immunization rate that we reach after 10 steps is double of the target immunization with a high waste of resources. So, after an extensive analysis and evaluation of several factors, we conclude we have found that average clustering coefficient is a good discriminant factor. What we have observed is that for low value of ACC, average clustering coefficient, then SR is better, so no stochastic reproduction is better, while SSR behaves better with a high value for ACC. So the deep analysis being conducted also using machine learning techniques. So the straightforward idea was to combine the two approaches in a new strategy, the general SSR. So we want to be able to adapt the strategy, the reproduction strategies to the type of network, and being able to choose either SR or SSR depending on the discriminant factor. Unfortunately, we cannot assume to know the average clustering coefficient, so the idea is to use a local estimation. So our approach was to avoid any global parameters and work in a setting in which the entities are completely distributed and have only local knowledge of the network. The average clustering coefficient is defined according to this formula, which is based on the quantity Ci, and I is a neighbor of a current node. So the idea is that each entity can estimate the average clustering coefficient by computing the average of the value C for all the nodes V which it has visited and their neighbor. So the general SSR algorithm has been designed by adding this discriminant condition. So if the average clustering coefficient estimation is lower than 0.6, then we trigger the reproduction according to SR strategy. Otherwise, we trigger the SSR stochastic reproduction. From preliminary experiments, we have found that 0.6 is a highly discriminant for the ACC value. We want to point out that in this approach, the entity takes completely autonomous decision at each step. They can adapt their reproduction strategy both to the graph and to the region of the graph where they are. The dataset we have considered in the experiment are taken from the SNAP database provided by University of Stanford. The dataset we have considered include the different number of nodes, edges, and values of ACC in order to verify the dependency and the flexibility of the algorithm in different situations. These are the final experiments that we have done to compare the general SR strategy to the previous two strategies. And the results are quite encouraging. This is the case of Facebook, where we have a target of 15%, and Facebook ACC is 0.6. And we observe that the behavior of the immunization rate is quite stable until 100 steps is still very stable. We don't observe anymore this behavior where the target immunization jump up to a very high value with a very high number of wasted resources. And this behavior is quite common to all the experiments we have done. Here is another case, Net7. Again, the target is 15%. Both algorithms were exhibiting this behavior of increasing the target immunization in the time. And here instead we have a very stable behavior again. So the reason of this phenomenon was that a few entities were still reproducing, too much entities. In our case instead, in the general SRR strategy, each entity is able to use either one strategy or the other, depending on the local environment that he observes. That makes this general SSR distributed strategy much more effective. This is again example of Nutella, where we were reaching a double immunization rate. We were able to reach the target immunization rate and still having the very stable behavior. As a conclusion, we have presented a new self-regulating adaptive strategy for network immunization which can work on scale-free network. The important thing, the important novelty is that the strategy is completely self-regulating. It doesn't need to know any network information, not even the number of nodes. Only the target immunization can be set as a rate, and the entities explore the networks and estimate the different values that they need. The strategy is fully distributed, it doesn't need any global information. And as a conclusion, the experimental results are very good on all the networks that we have tested. And they improve both strategy, SSR and SR strategy. Work needs still to be done, and we are currently doing parameters tuning in order to further improve the results. We are also planning experiments on dynamic network. The idea is to implement an algorithm which allows the entities to wake up, self-tune, and continuously explore the network for dynamical changes. Other interesting application we are considering is to apply the approach to other centrality measures. In this case, we are applying and computing the degree centrality, but in principle the same approach can be applied to other centrality measures. This concludes my presentation.